In the 2023 Decadal Survey, exoplanet astronomers came together and agreed that what they want is the Habitable Worlds Observatory, a space telescope capable of observing an Earth-sized world orbiting around a sun-like star. And I think you can understand why this would be amazing. I mean, finally, for the first time in human history, we could potentially get the answer to the question, are we alone in the universe? And this might be the telescope to do it. But there is a lot of technology that needs to be developed to get from here to there. Especially, how do you suppress the starlight by a factor of 1 in 10 billion so that you can remove the light from the star to reveal the much fainter light of this planet beside it? My guest today is Dr. Bertrand Mennesson. He's the Deputy Project Scientist for the Roman Space Telescope at the Jet Propulsion Lab at NASA, and I will explain why that is important in a little bit. And he's also the co-chair of the Technology Assessment Group for the Habitable Worlds Observatory. So enjoy this conversation with Dr. Bertrand Mennesson. Bertrand, give me a sense of how difficult it is to resolve, say, an Earth-sized world orbiting around a sun-like star with our current technology.
Yeah, so, that's one of the difficulties, right? It's not only that these planets are extremely faint, at visible wavelengths, these planets are about 10 billion times fainter than their host star. It's also that they are extremely close to them. So what we like to use in astronomy, of course, is this diffraction limit of telescopes, which is, when you make an image of a point in astronomy, the image is actually not a point, it's an extended source, which has its size being limited by what we call diffraction. And so the unit of diffraction is the wavelength divided by the diameter of the telescope. And what's very difficult is to observe very close to the diffraction limit. And so these planets are typically located at 2 or 3 times the diffraction beam width.
But if the star wasn't there, would the current generation of telescopes be able to get a single pixel of the exoplanet?
So yes, if the two objects, the star and the planet, were of the same magnitude, they would be further enough from each other that you could separate them.
With say Webb or
with
some
Webb,
ground-based
or even
observatory,
with Hubble in most cases. Hubble being working at visible wavelengths and Webb at mid-infrared wavelengths have about the same spatial resolution. One at 2 microns, the other one at 0.5 micron.
Right. So that we could resolve a 1 AU gap between two objects that are the same brightness with our current technology. Yeah, at 10 parsecs. Okay, like 30 light years. Okay.
Yeah, so the big deal is not only the spatial resolution, but of course the combination of that spatial resolution requirement, which is hard enough, but it's really the dynamic range, the contrast requirement, which is very difficult.
And give us a sense. I mean, we are familiar with, say, the TRAPPIST-1 system, where you're attempting to observe a red dwarf star with Earth-sized worlds orbiting very close to the star. We could think about things like Jupiter, and then we think about that sort of the dream of the Earth 2.0. Give us a sense of what is that sort of contrast in brightness between those kinds of objects.
Right. So the contrast is related to the separation. I mean, the closest the planet, the more it will reflect starlight at visible wavelengths. And then it's related to the size of the two objects. So for planets around TRAPPIST, TRAPPIST is an M star. It's a dwarf star. So it's a pretty small star, which not only makes transit measurements easier, like we're done with the TRAPPIST system, but would make the contrast a little bit easier in terms of the contrast problem. Now the planets are very close to the star, so it would actually be a very difficult system to even image with these giant telescopes. Now, when you compare Jupiter analog to a strict exo-Earth analog, if we were to look at the solar system from a distance of 10 parsecs with exactly the replica of the Earth at 1 AU and Jupiter at 5 AU, the Earth would be about 4 times brighter than the exo-Jupiter. So, dimmer than the exo-Jupiter. So nothing is easy as soon as you look for really mature planets. The planets that we discover today, that we have discovered and directly imaged today, are around these fairly young stars. And so the planets are still pretty bright from their heat of formation. And so it's more like one part in 100,000, one part in a million, maybe, at visible wavelengths. But for an exo-Earth, it's one part in 10 billion. So it's a much more difficult problem.
Right. We are talking many orders of magnitude to reach that 1 part in 10 billion. And so you've got to dim the light of the star to 1/10 billionth so that you then have those two objects that are the same brightness that are separated by that 1 AU that you can then resolve the gap in between them and image them.
Yeah, that's basically what we're trying to do. So once you cancel out the starlight, what's remaining of the starlight is no longer a point or diffraction limited point at the center of the field. It's what we call this field of speckles, which are all these starlight residuals that are spread out over the focal plane. And so they are brighter at the center where the initial star was before cancellation, and they get a little dimmer as you get further out. And at the planet location, there's still enough of it to be roughly at the same level as the planet. And so the next step, which is really important and something I'm trying to explain in a recent paper, is that it's hard enough to cancel the starlight, but that's not the end of the story. Because if you put a brick in the optical system, you would perfectly cancel the starlight, but there would be no planet light coming in. So not only you need to reduce the starlight, but you also need to make sure that the planet light is still going through unattenuated, and maybe even if it's slightly dimmer than the residuals from the star, that you're still able to distinguish planet light from residual starlight. And that's the whole field of post-processing or differential imaging, depending on how you want to call it, that really allows you, enables you to possibly even detect planets which are slightly dimmer than the residuals, the starlight residuals. And so
that's the whole game. I mean, this is,
Yeah.
In the 2023 Decadal Survey, astronomers said we would like to image or, do spectroscopy on the light from an Earth-sized world orbiting around a sun-like star, the Habitable Worlds Observatory, please. And now the challenge is to come up with a technology stack that will deliver that. And so the paper that you did that caught my eye was you investigated the various pathways for suppressing that starlight to bring that star and that planet down into being equivalent in brightness. And so, I'd like to spend a while now as we examine the different strategies that you have identified in your paper. So what is sort of like the first main technique that could be used to suppress the starlight?
So I would say at visible wavelengths, the main technique that's been used so far, visible near infrared, is really coronagraphy. And so in that case, the optical system that's going to cancel starlight is inside the telescope. It's really a series of optical systems, a series of pupil planes and focal planes with different masks, which are basically designed to control diffraction and scattered light. So the initial coronagraph was developed in the 1930s by Bertrand, just to look at the solar corona, which was kind of a similar problem. At the time, it just wanted to be able to look at the corona without, being completely blinded by the glare of the central star. And so it put this very simple system where, it's kind of intuitive. You would put like sort of a dot at the center of the field of view that blocks the central part of the sun in that case. And then you would have some light going around and actually being diffracted around it. And in a subsequent pupil plane, you would put the so-called yaw stop, where you would get rid of most of that diffracted light. So we've evolved a lot since these very early days, but the principle of coronagraphy is basically that, to manipulate the amplitude and the phase of the stellar light electric field to get rid of it and minimize it in the final science focal plane. And what really made it possible is the advent of adaptive optics in the 90s, because in order to reject starlight very efficiently, you need to be able to control the wavefront with very high accuracy. In the case of exo-Earth detections or spectroscopy, like we're talking about, at visible wavelengths, we need to control the wavefront at the level of picometers, tens of picometers. And so we need these deformable mirrors to correct the wavefront that is changing very slowly in space, not as fast as it does from the ground behind the turbulent atmosphere. But we still need an optical system that is kind of actively correcting the wavefront. That's the next generation of coronagraph that has never been flown so far.
And I want to sort of, a lot of my audience is very familiar with adaptive optics, but seen from the perspective of a ground-based observatory that's attempting, you shoot up the guide stars and you are attempting to remove the effect of the Earth's atmosphere by distorting the mirrors to account for the, how whatever object is wibbling and wobbling in space in front of you. But what you're talking about here is using adaptive optics, but still out in space. So you're not even having to compensate for atmosphere. This is still a necessary technology. So can you help me understand why adaptive optics, like what is actually causing the changes that your adaptive optics system is requiring in space?
Yeah, that's a great question. And when people started to work on adaptive optics, it was never, I think, thought at the time that it might be useful for space astronomy, because now you're above the effects of the atmosphere. You don't have to deal with that turbulence that changes the wavefront every 100 times a second, etc. So what's happening in space is very different in terms of temporal and physical scales. So what's happening is that as the telescope is staying pointed at a given target, a given star, the thermal load on the telescope will change slightly. Maybe the angle of the sun versus the telescope is going to change slightly. And believe it or not, that's enough to create some kind of thermal distortions that will induce some kind of bending or slight bending of the optics, or differential motion, depending on the thermal load that's being received by different parts of the spacecraft. So that's being seen as a slow and very small wavefront perturbations, which still needs to be taken out by a slow adaptive optic system. So that's why we still need some way to control the wavefront, and very, very precisely, even if it's every 100 seconds instead of 100 times a second.
And once again, when I think about the adaptive optics system that's used on Earth, it is fast that you have these pistons that are deforming the secondary mirror to account for the atmospheric perturbations, but it is changing many times a second to account for whatever it's seeing. So what is the actual, is it pistons? What is actually changing the shape of the mirror in space over this slower time frame?
So as I was saying, as the thermal load on the telescope is changing, it's changing pretty slowly, right? Because it's really related to how much heat you're getting from the sun, which is never, in your direction in your field of regard, but close enough that, one side of the telescope will be colder than the other, just because the sun is only on one side. And so as the sun is moving, or as your telescope is moving away or closer to the sun, this distribution of heat will change over the telescope. And so that's what creates these very slow changes in the shape of the mirror. It's basically coefficient of thermal expansion, right? So as the temperature changes by, we're talking millikelvins of stuff like that, or maybe tens of millikelvins between one place or the other over time. But that's enough to create these kind of slow wavefront aberrations and deformations of the optics.
Right, but what is the solution? I mean, I think we were all sort of on the edge of our seats watching as James Webb did its final focusing, and they were sort of showing us how they were bringing all of the different mirror segments together and aligning them, and all the underlying technology that would allow them to be sort of optimized to, and I forget the measurement, like micrometers, whatever it was. It was some incredibly small amount. Yeah. So what is the kind of technology that would be used to get that telescope into that perfect alignment that accounts for the issues with the wavefronts?
Yeah, so that's a great question to compare to JW, because JW did wonderfully. However, their wavefront stability, it's at the nanometer, few nanometers level, which is incredible given the size of the telescope. But here we are needing stability probably 100 times smaller or better stability, right? So in order to do that, you cannot do like you do on web, where once in a while they measure the wavefront and then it's set and forget for maybe a day, and then they remeasure it regularly, because you're observing at 10 microns. So if you have like your wavefront is 70 nanometer RMS one day and 72 nanometers RMS the next, that's fine. But for coronagraphy, we're on a different ball game, right? So what we do is like we have to measure that wavefront in real time all the time. So what we are using in that case is what we call a wavefront sensor, and there are plenty of different types of wavefront sensors. Like from the ground, when you use adaptive optics, you use some kind of Shack-Hartmann wavefront sensor to correct for these fluctuations. For coronagraphy, there's different types of low order and high order wavefront sensors that we are trying to use. I cannot really go into a lot of details here, but one of the best thing on Raman CGI that we're already going to try, we're going to be using a low order wavefront sensor that will sense these very small variations of wavefront and then feed them to deformable mirrors that are going to compensate for this in real time, over hundreds of seconds, something like that.
And so, so just to sort of catch people up so far, we've got the coronagraph, we've got, we're putting our thumb in front of the star, but, something in front of the star. The light is passing through. It is then being, run through prisms and grisms and all kinds of things to try and re-interfere the light with each other and remove every stray piece. And you're also deforming the mirror to adapt to how the wavefront from the star is actually changing over time. And how far does that get you? Does that get you to Earth-sized worlds orbiting around sun-like stars? Does that suppress that 1/10 billionth of the light?
So that depends on the environment, whether you're talking about the lab, whether you're talking about Raman in space, or eventually HW in space, which is the mission that we're after now. So in the lab, we are getting, that was one of the points in the paper, was to get a review of how well we're doing in the lab so far. In the lab, we are able to reject that starlight by, maybe a part in a few billions. So maybe not a part in 10 billions yet, but pretty close. And that's in the lab in as stable an environment as we can make it in the lab. It's in vacuum. There's no turbulence in the chamber. It's stabilized in terms of temperature, etc. So after that, how well you're going to be able to do in space is actually related to the telescope itself as well. I think one of the biggest difference between the coronagraph and any other kind of instruments that you can think of is that the starlight suppression instrument in that case is not just a simple back-end instrument. It really starts at the primary mirror of the telescope. So this is the whole chain that you need to optimize. So you need also to build the telescope for coronagraphy. If you just, take any kind of telescope and you say, well, I'm going to retrofit a coronagraph behind it, you're not going to get optimum performance. So it's really a joint optimization problem. With Raman, I think that's the biggest difference with Raman. With Raman, the main science case is dark energy and dark matter. This is a wide field imaging instrument. We got kind of a ride on it to try coronagraphy, and we are very thankful for that. But the rule of the game in that case was, well, you get a free ride in some way, but you can't place any kind of constraints or requirements on the telescope. So in that case, we had to optimize the coronagraph alone. We couldn't touch the telescope. So I believe that in order to get to this time -10 kind of contrast levels, we're going to have to really optimize the whole system together, the telescope and the coronagraph, and make sure none of them has an impossible job to do.
And so, with Nancy Grace Roman, this is one of those two refurbished telescopes that were donated to NASA. And so you didn't have a lot of control over that you didn't get to build it. The National Reconnaissance Office built that telescope. So I can see that, okay, you're taking the best possible case of a coronagraph that you can, but at the end of the day, you don't control the very beginning of that technology stack that you're putting there. It is a, you know, that part of it has been supplied. And so it's great that you can attempt your technology on this, but you have to work within those constraints. That's really interesting. So this sort of best level of starlight suppression you've been able to get into the lab, that actually really does get you within striking distance if you can also ensure that the actual primary mirror is part of the team as well.
Right.
From day one. Yeah, okay, I understand. So, that gets us most of the way there, but you considered other kinds of improvements in technologies to sort of eke out more, success in this. So can you let me know some of the other ideas that you considered as part of this paper?
Yeah, so I think maybe just before that, and one thing to clarify is that we are within striking distance, or maybe close to there, really close to there, in terms of what I call broadband detection. Is first you try to detect these planets. After that, what we are really after is spectroscopy. So, and that's when you're not just making a photometric measurements, but you separate your different wavelengths, and that's where you can start to look for molecules in the exoplanet's atmosphere. And so now, when you're talking about spectroscopy, you get much less photons available, and so you need to make a system that's probably even more efficient in terms of gathering photons and making sure you're keeping all of your precious exoplanet photons. So there's ways to do that with coronagraphs. I think one thing that we're going to have to demonstrate a little bit further is the ability to do this with segmented apertures. That was one of the big conclusions of the paper, is that yes, in the lab we've demonstrated pretty good performance already, close to what we need on simple monolithic apertures, but not yet on segmented apertures. So that's the first thing we're going to want to push. And after that,
segmented like James Webb.
Like James Webb, exactly. Right. If we want to be able to use segmented telescopes in the future, which are probably more scalable, than huge monolith, which have never been built above 3.5 meters at optical near-infrared wavelengths, it seems like we should be trying to get these measurements with segmented telescopes. And so that's kind of the baseline today for HWO. So we need to do a little bit more work in the lab on starlight suppression with segmented apertures. After that, for spectroscopy, we can certainly try to get more efficient coronagraphs, and there are designs in the works for that. Another instrument that's really different and kind of attractive that's been proposed in the past is the star shade. And so the difference is, for the coronagraph, it's really optics inside the telescope that are doing the hard work. In the starshade case, it's an external occulter. It's like a giant screen that flies in front of the telescope. We're talking a screen of 50 meters in diameter. It's like a tennis court size deployable structure that flies 100,000 kilometers away in front of the telescope, in the line of sight to the star. And so basically the starlight is being canceled in theory before it enters the telescope, just by this giant screen, which is based on finite diffraction theory, etc. So it's a very appealing theoretical idea, which has also shown some really spectacular results in the lab, but only at a very small scale. I was mentioning about 50 meter diameter in space is what we would be needing. This was demonstrated in the lab with a 5 centimeter aperture. So with a factor of 1,000 to 1 in there. It's never been used for astronomy or observational astronomy, while coronagraphs are being used on all major ground-based optical near-infrared telescopes. So it's interesting because it can do very efficient spectroscopy over very broad band at a given time. I mean, if you think about it, most of what's happening is doesn't depend on the exact wavelengths. You just have a piece of optic which is blocking the light at all wavelengths in range. So it's pretty attractive in terms of efficiency and the ability to work at very large bandwidths at once, which the coronagraph are working to achieve as well, but are more limited in.
But I mean, obviously, the downsides of this is it's a completely separate piece of hardware that could be successful or fail on its own.
Right.
And the distance between, if it's tens of thousands of kilometers between the spacecraft and the starshade, you don't get a lot of targets that you can direct your instrument at, because how often are things going to line up the way you need them to?
Yeah, so that's exactly the main restriction of the starshade, which is, each time you move from one target to another, you need to repoint the starshade. You need to move it in front of that next star. And we have limited fuel unless you can refuel the starshade. So unless you can refuel the starshade, you probably have 100 to 200 slews that are available to you, given how much fuel you can get. And so that means that first you need to devote the time to move from one target to the next, and then you have a limited number of pointings. So in fact, what's really interesting, I think, is that there's a lot of complementarity between the coronagraph and the starshade. The coronagraph is extremely agile. You can get hundreds, maybe thousands of pointings out of it, and so you can first use the coronagraph to detect these planets, make sure they are physically associated to the star, measure their orbits. Maybe you can get some spectrum, and then possibly you could get a broader spectrum more efficiently with a starshade on well vetted targets, and that's something that we had suggested in the past for one of these predicadal concept studies. Whether that's going to be a possibility for HWO, we don't know. I think right now we're baselining for sure a coronagraph. After that, we'll see if it's possible to and really advantageous to associate it with also a starshade that could be flown at the same time or maybe later once we know where to point it.
So were there any other technological advancements that you're thinking about as ways to further suppress the starlight, or is it just those two main categories?
So there was like another type of instrumentation that was proposed in the 90s, and actually I started my research in that field in the mid 90s, at the time where we thought that the best way to do this type of measurements was in the mid infrared. If you want to observe the solar system at 10 microns, guess what planet is the brightest in that system at 10 microns?
I'm going to guess it's Earth. Is it Earth?
Yeah, exactly. It's the
Wow.
Earth. Yeah.
So Earth is the brightest object in the solar system at 10 microns.
It's the brightest point source, in the solar system at 10 microns. So if you were to look at it from a distance, it's slightly brighter than Jupiter, and that's just because the Earth is at 300 Kelvin, and Jupiter is much colder, so it still doesn't emit too much anymore at 10 microns. So the idea back then was, well, let's make these measurements where the contrast ratio between the star and the planet is not as difficult to reach. So at 10 microns, the star is only 1 to 10 million times brighter than the exo-Earth. So that is easier. But now you're working at 10 microns. And so now, instead of getting away with a 6-meter telescope, you would probably need a much larger telescope or an interferometer with telescope separated by 20, 30, 40 meters. So that's what we tried to do at the time, and it's still being pursued to some degree. But that's
this was the terrestrial planet finder.
Right. So in the US, that was called the Terrestrial Planet Finder Interferometer. Originally, it was TPF. Then we started to propose the TPF coronagraph. But and in Europe, it was called the Darwin Space Mission, which was the dream of a few people, both in the US and in Europe at the time, and that got the field started. It may be that the first thing to fly is not that instrument, but it's a different instrument, a coronagraph-based instrument that will kind of provide a similar type of science. So the science remained, the technology has changed as it, we just after the simplest, most affordable technology that can do the job, whether it's a coronagraph or mid-infrared Nulling interferometer. We'll see. But for now, we are mostly targeting a visible coronagraph. Yeah.
Right. And I think, when you're flying an interferometer, then you have a similar version of the problem that you have with the star shape, which is that you've got two parts to the recipe, and they've both got to be perfectly aligned down to your 10 microns. They've got to be able to turn at the same time and be gathering data and picking up the same wavefront at the same time. There's a lot of issues. But do you need a coronagraph anymore if you've got that 10 micron telescope that is large enough? Do you still have to run a coronagraph?
Yes, for science reasons in particular, because it's fantastic to have both visible and infrared data and mid-infrared data, because they give you different information about the physical nature of the objects you're looking at. I mean, a typical example is that if you just look at a source in reflected light in the visible, you don't know if it's a big source with a small albedo, small reflectivity, or large source with a small albedo. So you have no real idea of the size. You only see the product of the albedo, which is the reflectivity of the object by its surface area. It's only when you go to 10 microns that you can actually look at the temperature. So the 10 micron part gives you the temperature. If you only have the visible, you may not get the temperature, and vice versa. There's information that you only get in the visible that you wouldn't be able to get in the mid-infrared necessarily. Like oxygen is visible in at 760 nanometers in the visible range. It's not visible in the mid-infrared range except for ozone.
So, I mean, let's say it was a single mirror. How big would it be, do you think, if it was just a single mirror mid-infrared space telescope?
So if it was a single mirror, you need to make it large enough that you got that spatial resolution. So I think it would have to be at least 20 meters in space, I think.
Okay. So, I mean, 20 meters isn't 10,000 kilometers. And so 20 meters, you could have a boom that is connecting the two. If it is two telescopes connected together, they could have a rigid structure that's attaching them together. And you've got a, I've done a lot of research into this, and there's some really neat projects out there that have been proposed as well. So
yeah, a lot of the best architectures and configurations have more than two apertures. They tend to have 4 plus a beam combiner, so it starts to be a bit more complex.
But still, you're within a 20 meter length as opposed to 10,000 kilometers, and you're having to. I think about LISA, right, where you've got these things that are flying at whatever tens of thousands of kilometers, and they're attempting to maintain this position to a level of perfection that they can detect these gravitational waves. So it's not that difficult an interferometer. He says, just dismissing the complexity. Okay, so that's a really exciting pathway. What else have you sort of looked into as a way to suppress the starlight?
So there are a lot of new technologies for coronagraphy that are being developed as we speak, that are being tried out. Whether or not they will come to fruition in time, is a very complex question. I mean, when you're at a stage where you're preparing for a future mission 20 years from now, there's always the question of how much you want to privilege the best current candidates versus the new kid on the block, which sounds promising from a distance, but you don't know if it's going to pan out. So you have to manage that portfolio of technologies that could potentially work. It's the usual saying that we tend to overestimate what's going to happen, how well we're going to be doing in 5 years, because we extrapolate from current technology and we are being too optimistic. But sometimes we don't really. We could actually underestimate what's going to happen in 20 years, because you don't even know what kind of technology are going to appear in the meantime and be very disruptive. So we're trying to look at other possible technologies for coronagraphs, like photonic based and things like that, photonic lanterns, and we'll see how far we can get with these. But we also have some really good candidates now we want to push.
Well, I mean, I'd like to go through a few of them. Like, we talked before this episode began about nulling. This is the idea that's been suggested for the large interferometer for Exoplanets mission. And that's going back to this idea of the terrestrial planet finder, but let's use this idea of nulling. So can you explain how that would work?
Oh yeah, so nulling is kind of magical when you think about it, because it's light plus light equals no light. So it really uses the wave nature of light, right? So if you take light coming from the same source and recombine it coherently but out of phase, then you're going to have some destructive interference. And so basically you point at the same star with two telescopes, and then you recombine the beam with a pi phase shift. And in principle, you get a complete destructive interference state. So that's why it's called nulling interferometry. So that was developed essentially at the Keck Observatory. That's a place where we built a mid-infrared nulling interferometer, and it's also been built at the Large Binocular Telescope in Arizona. So we thought it would be precursors to a future mission. That was not the case, but it was still used to retire one of the big possible obstacle to the detection of life around around other stars, which was the fact that there's exosidal called dust in this system. So, and it's something you can see very well in the mid-infrared. So what's happening is, as you look at these exosystems, so you got the star in the middle, you got the planets, but that's not all there is. There's also a lot of dust that still remains from comets passing by and asteroids, in the central system. And when you look at it from a distance, even though this dust is not very dense, it still creates a very strong background. And so we were worried originally in the 2000 about how bright that background might be. And so there were a number of instruments that were built, and we built here one at JPL, and another one was built at the University of Arizona to look at this problem, and we were able to retire it. So even though nulling interferometry was not used for detecting exo-Earth, it was still used to retire one of the biggest issues that we thought would be possibly a problem for exo-Earth
That's
detection.
interesting. And then you mentioned photonic candles. I've never heard that before.
Oh yeah, so it's photonic lanterns. So
photonic lantern.
I'm not either very familiar with it, but it's a variant of a special filter where you actually inject light into a lantern, which has a number of modes that can be separated and feeding single mode fibers. So it's kind of a new technology, and it's been proposed also to be mated to a regular coronagraph, and it could be also directly used as a reference sensor. So it's something that's being worked out.
I think about, like, say, with LIGO and with gravitational wave observatories, because they've been able to, and same even with the Large Hadron Collider, they're able to do separate runs, and then each time they come up with a bunch of really clever ideas, like with quantum squeezing, so that they're able to take advantage of quantum effects to be able to get the kind of data that they're interested in. I mean, it's great that Roman is going to be equipped with the state-of-the-art chronograph that is currently existing. So when Roman is operating, what are you going to be looking for that will inspire that next round of changes so that you can kind of tweak your engineering?
Yeah, so I think one of the things they want to check with Roman is that our models are right. So there's going to be a lot of model validation. Are we actually seeing the performance that we expected? Because then that shows that our models are correct, and so we are then more inclined to believe them when we use them to prepare for HWO. And that's models of the telescope, models of the coronagraph itself. So that's one of the first things we're going to be looking at. Another thing is, now we're going to have this space test bed in a way, right, with Roman. And so we're going to hopefully be able to try some post-processing methods. So, when I mentioned at the beginning that once you've extinguished the starlight as much as you could, you're not done yet. You still need to be able to dig the signal of these planets, which might be even fainter than the residuals. There are plenty of ways we think we can do that. One have to do with what we call angular differential imaging, which is to rotate the telescope, the planet moves and not the speckles or stuff like that. But there are also other methods which have been suggested that would be extremely powerful potentially for HWO. And has to use actual data taken by the reference sensor at the same time as the science focal plane images, and use one to calibrate for the other. And so that's kind of a dream a little bit, which is there are two ways to be able to take out the starlight residuals in the focal plane. One is to make sure that they're extremely stable over time. And so now if you observe another object, you can subtract one from the other, and if one has a planet and the other one doesn't, then you win. But that puts a huge primer on stability of the system, because it means the system needs to be perfectly stable. The other way you could do this is say, well, I don't care so much about stability, but I need to know how it fluctuated. And so if you can actually do this, then maybe you don't need to be as stable as you think. So that's the kind of, it's very detailed and technical, but that's the type of things that we hope to learn with Raman, which place on that continuum between infinite stability and pure knowledge we're going to end up at, because they will have a huge impact on the design of and the requirements on HWO.
Right, but it'll be like you'll be actually using this coronagraph and understanding how to get the most out of the system, making whatever software tweaks that you can to see if you can get more of the kind of information that you're looking at, and then think about how you can then, on your next iteration for HWO, bring those techniques into hardware, into actually building them and improving the actual optics in the system so that it does this by default, as opposed to it being a patch that you've figured out after the fact.
Yeah, exactly. I mean, we hope to have a lot of lessons learned from Raman CGI in terms of how to make the next coronagraph even better, because it's going to need to be still better than this one. But once again, using a telescope that is more coronagraph friendly will also help us. In a way, getting to the performance that we think we can get out of Raman CGI might be good enough in terms of control for getting pretty similar results with HWO. So having an optimized telescope will help with HWO.
So I want to sort of unshackle your imagination now for a second here, because you're sort of working within the existing constraints and the concerns of the decadal survey and all of that kind of stuff. But, if money was no object and you had a sort of, napkin in front of you, what would be like the dream machine to be able, because I think finding evidence of life on another world, another Earth-like world, would be one of the most profound discoveries in the history of science. And we are now in striking distance of having an answer to that question. We are 20 years away, maybe, from knowing, pointing to a star and going, there's life there. What would be, is it a better coronagraph? Is it a bigger mirror? Is it an interferometer? Different techniques? What would sort of take us to the perfect life-finding space telescope, do you think?
Right. So I may give you an answer that you don't expect, but I think it's a combination of a lot of different instruments, not just one. And that's what we've seen a little bit in the past. Once you start to find an object of interest, all of the telescope that can actually observe it and bring something new to the table will do it. And I think that's going to be a little bit the case here. So we're still at the start of all this. So what's going to happen is it's very hard to make an unequivocal detection of life, right? Unless you are there and you see some, grasshopper jump or somewhere, We're not going to get that. But what we're going to get is a lot of information that is very suggestive of life, or that we can't understand without the presence of a biosphere. And people will endlessly debate this. But one thing for sure is the more information you get, the better your likelihood of understanding what you're saying. So I think that the answer is a combination of instruments that would be both observing at visible near-infrared wavelengths and all the way to the mid-infrared. So I would like the whole slew of having a spectrum going from the near UV to the mid-infrared would be ideal. And I think piece by piece, we will get there. And if the US wants to work on the visible near-infrared part of it, and Europe wants to lead a mid-infrared part of it, and nothing against that. That'd be perfect. For all of these objects for which we're going to get data over the whole range, that'd be fantastic. And after that, you could always dream of, yes, eventually much bigger telescope that would basically be able to look at, get maybe resolve maps of continents and weather patterns, and looking at photometry fast enough that you can look at the alternates of day and night, and this that's endless. The physical characterization that you can get is going to improve over time, I think. But so my dream would be a panchromatic observatory that gets us a lot of data spectrally and with high spectral resolution.
So
everything.
So how big?
Well, eventually,
10 meters, 20 meters?
Yeah, I mean, if we could do a 20 meters telescope that might work from the near UV to the mid-infrared all at once. It's never been done so far because
I think that
it's
was
hard to work the cold with the near UV or the far UV. But
I think that was the dream of LUVAR, right? Which was that you could have a 15 to 20 meter telescope that goes from infrared through to near UV, and just like as one of its side jobs, it could be imaging Earth-sized worlds orbiting around sun-like stars, but also observing all kinds of other things as well. And so back to more like Hubble, a Swiss Army knife that can be used for all kinds of things, not just. Yeah. And so right now, really, it feels like with the Habitable Worlds Observatory, it has one main job, which is to see those Earth-sized worlds.
I may not put it exactly like this, because I think that it may have like one primary driving goal, which is it will be optimized for this. But then, once you've optimized your telescope for that type of detection and observations, I think that telescope is extremely powerful in many other areas of astrophysics. And so, it may be optimized for this, but then among all of the possible choices, you can still, put behind it a lot of instruments that are going to be transformational in general astrophysics, in galaxy evolution and formation, circumgalactic measurements, etc. So I think we can still do a lot of general astrophysics with this, and it could be over 50% of the time, because as you are pointing for 3 weeks to get your spectrum on an exoplanet, if you have 3 or 4 other instruments, that's a huge deep field that you can get.
But I think about, like, with Webb, we're seeing just 10 different targets a day, right? And then we're getting all of these papers coming out, going to archive. I mean, we're all reporting on many Webb observations every week. But with, say, the Habitable Worlds Observatory, it's like, what's it up to? It's still looking at that one planet, and has been doing so for, as you say, for 3 weeks, for a month, because you're going to need that long term on that one target to get those answers that we need.
Yeah. I mean, for spectroscopy, it's we could be in that range. Yeah. So you would look at, but the good news is, if it should probably be, there will be cases where there are several planets in the system. So you will get fantastic measurements not only on the exo-Earth in that system, but on all of the other planets at the same time. So that's
totally. Well, Bertrand, what are you obsessed with right now?
Well, right now I'm obsessed with making a HW a reality, right? I feel like I'm having a second bite at the cherry because I used to work on TPF and Darwin and these other missions in the past. We are lucky enough to have another possibility here, and so I feel like we're all on giant shoulders here. There's been people thinking about this and dreaming about this for generations, all the way back to Carl Sagan and so on. I was very fascinated by Voyager, etc. at the time, and now I feel like it's our turn to deliver. We have lots of young students coming here and telling us, well, this whole search for life theme is like their Apollo program. It's the Apollo program of the 21st century. So I have a little responsibility in there to not disappoint them. So my obsession is to make sure that yes, for this, help the community to get together and make sure that we collectively get to that. And it's a fantastic adventure because it's not only scientific and technical, right? It's people. You can't do any of this without thousands of people. Web has shown it, and it is just really fantastic to work together on a common goal that's bigger than everyone. So my obsession is to make sure that we don't miss up that opportunity this time.
Well, it's funny, if you watch, like, I don't know if you remember From the Earth to the Moon, which was this show on HBO, and at one point they said, okay, gentlemen, everyone in this room, one of you is going to be walking on the moon. And, you've seen versions of this in science fiction where you're in this auditorium of new astronaut candidates and you say, one of you is going to be the first human being to walk on Mars. And I think you can make the equivalent case to the young scientists that you're working with today who are beginning their career now.
Fantastic.
You're going to be part of the team that is going to find evidence of life beyond Earth. And it's as you say, historic and meaningful a discovery that a human being could be involved in.
Yeah, that's an incredible opportunity to be able to say, maybe you made a difference. And it's very possible. And,
yeah,
sometimes young people come, I don't believe that they will be actually the ones making a difference. But that's what we need.
Yeah. But it's so binary. I mean, obviously there will be inconclusive results, and people will argue for decades about whether or not this was actually found, and they'll continue to refine their whatever are their signals of life and so on. But it is still this sort of one of the most important pieces of scientific work that humanity has ever attempted, and to know that we are now mere decades away from hopefully getting an answer, or at least getting a null result that gives us a sort of better perspective of how special life is on Earth. As Arthur C. Clarke said, either possibility is equally terrifying and I think exciting. Well, Bertrand, thank you so much for taking the time to chat with me today. I really appreciate it. And good luck with both the chronograph that's flying on Roman and the work in making HWO a reality.
Thank you very much, Fraser.
I hope you enjoyed that interview with Dr. Mennesson. It was great to hear exactly how they're hoping to accomplish suppressing the starlight. Now, I'm going to give you some more thoughts after this, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chipolin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. So I want to give you some takeaways from this. So the first thing is that we have a couple of technologies that we can use to suppress the starlight of a star. You've got the coronagraph, which there's one inside James Webb. There's going to be one inside the Nancy Grace Roman telescope. There's ones inside other various telescopes. This technology is well known, but the advantage with habitable worlds is they'll be able to actually engineer the primary mirror to work in tandem with the rest of this coronagraph stack. You have the idea of the star shade, which is going to be floating away from the spacecraft and will be suppressing the light before it even gets to the telescope. And then you have this idea of nulling, where you are using two separate telescopes that are observing the same star, and they are canceling out each other's light so that they're then revealing just the planets beside them. And then finally, you've got this idea of observing in a different wavelength, where Earth is actually the brightest thing that you can see. And so you don't need to suppress as much starlight. And so who knows which of these technologies is going to end up being the one that really gets the job done. However it gets accomplished, when that next generation of technology comes along, when we get that habitable worlds observatory, we will have the capability to observe out to tens of light years around us and to be able to resolve an Earth-sized world orbiting around a sun-like star long enough to get the light so that we can do spectroscopy on that planet and to be able to detect the presence of various biosignatures in the atmosphere of that world. Is there ozone? Is there oxygen? Is there carbon dioxide? Is there methane? Other kinds of things in that world. And then astronomers can argue about whether or not that is indicative of life or not. Who knows? It may take decades to finally get an answer, but we are that much closer to getting the answer to this most profound scientific question. Are we alone in the universe? And hopefully, this is how we'll find out. All right, I hope you enjoyed this interview. We'll see you next time.